Today's topic is orthogonality. We are going to introduce the concepts of orthonormal bases, orthogonal matrices, and then we'll get into orthogonal projections. We'll start with the definition of an orthonormal basis. Implicit in our previous discussion was an idea of an orthonormal basis. A collection of vectors is orthonormal if they are mutually orthogonal, that means perpendicular, and every vector in the collection is a unit vector. You'll recall that a unit vector has length 1. So the 2 norm of x is equal to 1. Of course, the 2 norm is the square root sum of squared elements in x. So what's the easiest example of an orthonormal basis? Well, the elementary basis vectors, right? We tend to think of a two-dimensional plane having spanning basis vectors 1, 0, and 0, 1. Again, the axis would be the span of the basis vectors. And similarly speaking, in three-dimensional space, we would think about the x direction, the y direction, and the z direction. Now, this means in four-dimensional space, there's a fourth axis perpendicular to the other three. Of course, we'd be adding an entry in each of these vectors and a fourth vector that would be 0, 0, 0, 1. That's hard to conceptualize visually, of course, because we are three-dimensional creatures, but mathematically, it's really not problematic at all. Now, what if I want to change the basis to the red and blue directions shown, but I still want it to be orthonormal? Well, the two vectors under consideration are mutually perpendicular, so that satisfies the first part of the definition, but I also need them to be unit vectors. Well, that's no problem. I just need to find the unit vector that points in the direction of each. To do so, I calculate the norm of each of these vectors, which would be the square root sum of squared elements, or the square root of 2. And I simply divide each element in each vector by the norm of that vector. So these two vectors shown here form an orthonormal basis for R2. Now, why am I making a point about this? Well, the first reason is that there are infinitely many basis vectors to specify an axis, because the axis is just the span of the basis vector. So any vector that points in the positive or negative direction of that axis will specify the axis. But the computer is always going to provide a unit vector. And there are more than one reason. There's more than one reason for this. But the main reason is that we want the coordinates to tell us how far to go in each direction, meaning how many units do I walk in each direction. And this only works if those basis vectors have length 1. Recall that coordinate pairs are represented in a basis, and each coordinate tells you how far to move along each basis direction. Okay, so this is what I mean when I said it was implicit in our previous discussion, because this only works if E1 and E2 are unit vectors. If instead, you can imagine I chose a different basis vector for E1, perhaps the blue vector that's shown here. Well, how far would I have to move in that direction if I was going to the purple point? Well, if I were to choose this blue vector that's now shown on this page, I would only have to move 1 times that vector, and then 3 times E2. But 1 times E1 is not referring to how many units I walk in this direction, because it is quite clear that if there were a grid, I would be moving 2 units. So that's the main reason why we need that part of the definition for orthonormality. Now let's move along and talk about how we determine if two vectors are orthogonal. Again, orthogonality means perpendicular. So just when the angle between the vectors is 90 degrees. Well, great, we'll just take out our high dimensional protractor and measure. Just kidding. What we do is we use a formula for the cosine of the angle between two vectors. And it's given as the inner product of their unit vectors. Now, when you're looking at this, you might be confused by the second part of this definition, the inner product of their unit vectors. But keep in mind that the norm of x and the norm of y, that's their length, that's just a constant. It's just a number. And so because it's a constant, we don't have to really worry about where we put it in this equation. And so this equation is equivalent to writing the expression shown here. Okay, and this is the unit vector in the direction of x. Because all I have to do is divide every element in x by its norm to get the unit vector in the direction of x, just like we did on the previous example. So it's the inner product of the unit vectors of pointing in the direction of x and y. Now, the number cosine is between -1 and 1, and the vectors are linearly dependent when the absolute value of cosine is 1. So if cosine of the angle is 1, then those two vectors point in the same exact direction. They're overlapping. And when cosine is -1, those two vectors point along the same line, but in opposite directions. This is not the last time you'll see cosine. This is also a common measure of similarity for high dimensional data like text. And we can talk a little bit more about that later if you'd like. For now, we want to stick to the definition, and since we're talking about orthogonality, we're interested in the case when the angle is 90 degrees. Now, if anyone was a hotshot in trigonometry or even in calculus, they will remember their unit circle, and the cosine of 90 degrees is 0. And in order for this expression to be equal to 0, it must be the case that the numerator is 0. So two vectors are orthogonal when their inner product is 0, when x transpose y is equal to 0. Let's get a little bit of practice with this, and we'll come back in the next video.